Hello, and thanks for checking out Chemistry Connections on the Hopewell Valley Student Podcasting Network, a proud partner of hvspn.com, where students come together to publish content to share with the world. The opinions represented within this episode are those of the content creators only. Please enjoy the show.
Welcome to Chemistry Connections. My name is Mahisvi Vemulapalli, and I am your host for episode 9, The Chemistry of Chemotherapy. Today, I will be discussing how chemotherapy works in the human body. Before we talk about chemotherapy, we need to know what cancer is. Cancer is a disease where damaged DNA results in cells overproducing and spreading to other parts of the body, resulting in the gathering of a tumor. These tumors latch onto the body parts to surrounding cells, growing exponentially in size and taking over the body's systems. In order to combat cancer, chemotherapy was applied. However, the origin of chemotherapy comes from the discovery of reduced white blood cell counts after people were exposed to nitrogen mustard during World War II. Before you guys get excited about mustard, no, it is not the mustard that you eat. Nitrogen mustard was used in chemical warfare during the war as blister agents so that soldiers would get itchy and would not be able to combat any further. Although the intentions of nitrogen mustard were to harm their opponents, the discovery allowed researchers to start examining the therapeutic effect of mustard agents in treating lymphoma, a type of cancer that arises in the lymph nodes. Though more nitrogen mustard had to be utilized, it was proven that the patient's tumor masses were significantly reduced, marking the start of the use of cytotoxic agents for the treatments of cancer in 1946. Chemotherapy, otherwise known as chemical healing, started its fame that year. Therefore, as forms of chemotherapy updated and become popularized, there was a decline in mortality rates, making this treatment the most common for cancer. So today, we will be focusing on paclitaxel, a chemotherapy drug used for breast, lung, and ovarian cancer. And keep in mind, in a lot of today's pop culture references, whenever someone would be talking about cancer, a lot of people also talk about chemotherapy. So, using that as our information, we should understand how truly significant chemotherapy is. So, let's unpack the mysteries of chemotherapy. We're going to specify on paclitaxel for today, just because it's our chemotherapy of the day, but keep in mind that a lot of the components that are in paclitaxel can be applied to various chemotherapy drugs. So, let's talk about paclitaxel. Paclitaxel is a part of the bark of a Pacific yew tree. A yew tree is a type of pine tree that grows on the Pacific coast, hence its name. And one fun fact about yew trees are its fruits bear a lot of disgust towards them, so for humans, it's best not to eat the fruits unless you want to vomit. So back to paclitaxel. Paclitaxel is actually a tetracyclic diterpenoid, which essentially means that it's an organic non-metal compound with a base of 20 carbons, and many more carbonic structures on top of that. In fact, paclitaxel contains 47 carbons, 51 hydrogens, 14 oxygens, and 1 nitrogen atom. That's a lot of atoms. Based off of its molecular structure, this molecule mainly forms London dispersion forces, LDFs, with fewer hydrogen bonds. So let's talk about the molecular structure of this tetracyclic diterpenoid. Essentially, a lot of these organic compounds have a structure where it has its carbons going in a cycle, and around those carbons are mainly its hydrogens. In order to form hydrogen bonds, you need to bond with a H-NOF atom, which is the nitrogen, oxygen, or fluorine. In our compound itself, we only have one nitrogen atom, and we only have a few other oxygen atoms that are floating around. So the hydrogen bonds that are just floating around and essentially trying to gather in on this tetracyclic diterpenoid cannot make it on all of the oxygen bonds there and all of them becoming hydrogen bonds. So therefore, it may seem like there should be more hydrogen bonds, but again, due to the established diterpenoid that we talked about, where there were 20 carbons, it can't be distributed as much. So Coming back to the point about the London dispersion forces and its over-intermolecular forces, there is a greater LDF force when you have structures as such. Paclitaxel itself is originally a fine white powder. In order to administer as an injection, it needs to be dissolved in a soluble solution. Paclitaxel is not soluble in water. Why? This is due to its organic structure that contains mainly LDFs. Therefore, paclitaxel is mainly a non-polar substance that can only dissolve with other non-polar substances, like methanol, for example. By dissolving the drug in methanol or other forms of alcohol, it can be administered as chemotherapy as it is injected into the human's bloodstream. So, since we talked about how chemotherapy is first created and then administered, let's talk about what it does once it's in the body. So, paclitaxel itself breaks down in the body by targeting dividing cells. In order to do so, paclitaxel goes through a biphasic decline. It has 2 stages. It works rapidly and consistently in its first stage, then it travels slower at a constant rate in its second change. In its initial elimination phase being the first stage, paclitaxel has a half-life of about 3 to 14 minutes, while in its slower phase, it has a half-life of around 13 to 52 hours. But let's talk about what this half-life is anyway. Half-life is the time required for a substance to reduce to half of its initial value. This means that in the case of paclitaxel during the first phase, it takes between 3 and 14 minutes for the initial dose to be reduced by half. Therefore, when the paclitaxel decomposes into the cells in order to break them down, they initially reduce to a faster constant half-life, and then break down further into a slower half-life. Once the molecule is fully administered, it can produce the greatest effect it needs on the human body. So now that you guys know how drugs like paclitaxel are first created and administered and how they work in the body, it's truly important to understand how chemical treatments like chemotherapy work in the body, as most people just attribute the treatments to losing hair as they've seen on, again, TV and other forms of entertainment. However, chemotherapy itself is a wonder, as it is one of the most efficient and effective treatments of cancer. Therefore, chemotherapy should not be taken lightly, and instead, it should be researched so people are aware of the multiple factors that might change their lives. Personally, I enjoy researching medical solutions, and understanding this popular treatment was eye-opening. So, the next time you hear about chemotherapy, I want you guys to remember its journey throughout the human body. And if you guys are interested in other forms of chemotherapy, go for it. Research on your own. There are many different targets that chemotherapy works on, and it is still evolving in its stage. Ever since the 40s and now even in 2024, it still has a pattern, but people are trying to attribute better conditions. However, it's also memorable that we were able to have such an efficient form of treatment for chemotherapy in the modern day. Thank you for listening to this episode of Chemistry Connections. For more student-ran podcasts and digital content, make sure that you visit www.hvspn.com.